Hey everybody, and welcome to our 11th video lecture. Today we're going to be talking about parametric surfaces and how to calculate their areas. Now you've already seen some calculations of surface areas back in your previous calculus classes, especially when the surface was the plot of a single function. But just like parametric curves can be much more complicated than graphs of functions, parametric surfaces can be a lot more complicated than their counterparts, and we can still come up with ways to calculate their surface areas and to think about them, and also just to graph them. Let's start by thinking about parametric curves. So to describe some sort of curve in R3, I give you a function r of a single variable t, which has an x-coordinate, x of t, a y-coordinate, y of t, and a z-coordinate, z of t. And if I'm thinking about t as the time, then as t changes, I go from my starting point, and I could spiral around and do all sorts of fun and crazy things over three-dimensional space, depending on what the values of x and t and y and t and z of t are, and end up somewhere at my ending time. Now, a curve is a one-dimensional thing, and this is indicated in a lot of ways, one of which is the fact that it just involves a single variable, or a single parameter, t. For a parametric surface, the big difference here is that we're going to have two different parameters. So for a parametric surface, I'm looking at a function r, which is not a function of t, but rather a function of two variables, u and v. And it has values, which are x of u and v, y of uv, and z of uv. So for one example, I can think about the parametric surface described by r of uv equal sine of u cosine v, sine of u sine v, cosine u. And I'm kind of wondering here what kind of surface this draws out as I let my parameters range. Let's say u ranges between 0 and pi, and I'm going to let v range between 0 and 2 pi. So what kind of surface does this draw? Well, if I think here, this first coordinate is my x value. The second coordinate is my y value, and the third is my z. And if I calculate x squared plus y squared, this is going to be equal to sine squared u cosine squared v plus sine squared u sine squared v. I can simplify that as sine squared u times the quantity cosine squared v plus sine squared v. And of course that's the same thing as just sine squared u, which if I look at what z is the same thing as 1 minus z squared. So every point on this surface is going to satisfy the equation x squared plus y squared plus z squared equals 1. So I'm looking at a surface which satisfies this equation x squared plus y squared plus z squared equals 1, and that immediately should make us think about the sphere. And specifically the sphere of radius 1. And what this says then is that the surface that I'm drawing is going to have to be at least it's going to have to lie on the surface of the sphere. It doesn't necessarily have to be the whole sphere. We don't know that yet. But if I also think now about spherical coordinates, in the spherical coordinate system, to write down a particular point on the sphere of radius 1, I'm just going to take rho to be 1, and I'm going to let phi and theta be whatever they want to be. So the corresponding points on the sphere are all of the form sine phi cosine theta, sine phi sine theta, cosine phi, as in the spherical coordinates, phi ranges between 0 and pi, and theta ranges between 0 and 2 pi. So this is exactly giving me the whole sphere because it's exactly how we describe the sphere in spherical coordinates. Let's look at another example. In this example, I'm going to let my parametric equation be 2 cosine u, v, and 2 sine of u. In this case, I can check that my x value and my y value here will be related. And specifically, I can see right away that x squared plus y squared is always going to be equal to 4. So this is going to be a surface which lies on the cylinder in three-dimensional space, described by x squared plus y squared is equal to 4. Oh, and I'm being silly, aren't I? This is not y, this is z, isn't it? So it's x squared plus z squared equals 4. So this is a cylinder which is going to be centered around the y-axis. Like so. And the radius of the cylinder from the y-axis, the radius across is going to be 2. And since there's no restriction here in the value of v, I'm not demanding that the range of v be between any two values, the cylinder goes on indefinitely in both the negative y and y direction. And I also haven't restricted u, so I go around completely full circle, and I get the entire cylinder here described by the surface. As a third example, let's think about the parametric equation describing a surface given by cosine u plus cosine v, sine u plus sine v, and v. Let's try to plot this. This time it's harder to get an equation that describes a relationship between x, y, and z in a shape that we're familiar with. In fact, this is because the shape that we're going to make is not one of the shapes that we are familiar with. But what I can do here is I can choose, maybe a specific value of v, such as v equals 0, and see what u does when for that fixed value of z. So when v is equal to 0, I get this equation of a certain curve on my surface. This curve is given by r of u0 equals cosine u plus 1, sine u, and 0. And this is actually a parametric equation describing a circle in the xy plane. It's not a circle centered at the origin, but it's a circle centered at the point 1, 0 of radius 1. So let me draw that circle in here like this. And I can do that similar sort of procedure. I can also see what happens when v is equal to another number, say pi over 4. And this is going to describe another curve on my surface. And it's given by cosine of u plus the square root of 2 over 2, sine u plus the square root of 2 over 2, and pi over 4. So this is going to be a circle in the plane z equals pi over 4, which is again a circle of radius 1, but it's centered at the point root 2 over 2, root 2 over 2. So it looks something like this. And then similarly, I can do when v is equal to pi over 2. And in this case, I get r of u pi over 2 equal to cosine u sine u plus 1 pi over 2, which is going to be a circle which is centered at the point 0, 1 pi over 2 in the flat plane z equals pi over 2. So it's a circle up here. And continuing on this way, we end up with a lot more circles, which are following a pattern of rotating around the z-axis. So what the actual surface is doing is it's forming a tube which encapsulates all these different circles, but rotates around the x-axis, kind of like one of those fun slides you see at the playground that corkscrews around a little bit, like this picture I've included right here, where it's spiraling around some axis, like a z-axis, which is in the center of it here. And that's what our plots were showing us. So yeah, that's definitely not a surface that we are familiar with an algebraic equation for, but it's one that we can plot using parametric equations for surfaces. So this is like a pretty cool tool that we have. One of the things that we'd also like to be able to do is to go the other direction, and that is, given a surface, I would like to be able to find a parametric equation which describes that surface. And one of the interesting things, of course, about parametric equations is that there are lots of different parametric equations which describe the same object. This was definitely true for curves. When I was thinking about parameterizing a circle, there were a lot of different ways I could do that, or a line, or anything like this. And surfaces are more complicated than curves, so they have that many more different parameterizations. For example here, I can think about the cone described by z equals the square root of x squared plus y squared. Graphically, this is just this upper part of a cone, so it's not the lower half at all, because I've already taken the square root and taken the plus part. But this is the surface that I'm describing. And there are a couple different ways to parameterize this. One feasible parameterization is just to take r of u and v, and I'm just going to let x be u and y be v. So it's the most obvious parameterization in the world, and then in order to get my surface, I'm going to have to let z be the square root of u squared plus v squared. And this is a very nice, easy way to parameterize this thing. But it might not be optimal in the sense that sometimes we might have to use our parameterization to do integrals or something like that. And then in that particular case, I might end up having to integrate square roots here, which is not a pleasant experience. So we might want to find a different sort of parameterization, maybe one that involves trigonometric functions, because sometimes that might make problems that we have to deal with easier. And I notice here that there's some symmetry in the sense that at any particular z value, I've got a circle of a certain radius. At that particular z value, I'm actually getting a circle of radius z. So this gives me the idea for the parameterization, r of u v, where I'm going to let my v value be z. So z is just going to be v. And then at that particular point, I need to describe a circle centered at the origin of radius v. So I can do that with v cosine u, v sine u. Now, on this particular parameterization, I need to be careful because I don't want to allow negative values of z because I'm only doing the upper half of the cone there. So I'm going to also specify v is greater than or equal to 0, and that makes sure that my z value there, that third component, will always be positive. And I can limit my u values to go between 0 and 2 pi, because if I do any more than that, I'm going to loop back around again and again and again, and I'll sort of like over-parameterize my surface. So this latter parameterization can definitely be very useful in comparison to the previous one, just because there aren't any square roots anymore. The previous example was a special instance of something we're very familiar with, called a surface of revolution. Now, I'm not talking about revolution in the sense that we're going to go grab our muskets. I'm talking about taking a curve, say some sort of curve in the xy plane, and I'm going to spin it around either the y-axis or the x-axis. And I could also spin it around the z-axis if I'm thinking about some curve in the xz plane or the yz plane. Let's just think about here spinning this around the x-axis. And when I do that, I generate a surface. And we've been talking about, even back in Calc 1, we talked about how to calculate the, say for example, the surface area of objects like this, and that sort of thing. But we can come up as well with parameterizations of these sort of objects. And the basic idea here is if this curve is given by y equals f of x, then at any particular x value, I need to be able to produce on the surface here a circle which has radius given by f of x. So a natural parameterization for a surface of revolution like this is r of uv is equal to, well here I'm going to let x just be v, and then in the yz plane, in this particular case by the way, the z-axis will be coming out this direction, so it's a little bit different than what we usually do when we're drawing these things. But in the yz plane, I'm going to be generating a circle of radius f of x. And to do that, of course, I can use sines and cosines. So I can just do x, which is v, so it's going to be f of v cosine of u, and f of v sine of u. And I can even limit my u values then to go between 0 and 2 pi, because that'll pick up the full circle there. And that way at any particular v value in the yz plane, I'm generating a circle of radius f of v, so this will parameterize my surface of revolution. And if I just want to go and do a finite surface which starts at a particular x value and stops at a particular x value, I can also bound v. And, of course, I could rotate around the y-axis instead, or I could rotate around the z-axis. And the parameterization is going to be a little bit different, but very, very similar. For example, the previous surface was a surface caused by rotating this line here, this straight line which forms the edge in the yz plane, just rotating that around the z-axis. So at any particular z value, so v I'm fixing to be v, I'm picking up some sort of circle of radius f of x, and f of x here was just y, or z, which was v, and it wasn't f of x, it was f of y. But yeah, so I was just rotating that curve z equals y around the z-axis. Now one of the wonderful things that having a parameterization of a surface does is it helps us to calculate the tangent plane of a surface. We were talking about tangent planes of the surfaces much earlier in this class when we were thinking about gradients and things like this, but there are surfaces we're given by we're given by just algebraic equations like x squared plus y squared plus z squared equals 1. Here I want to think about tangent planes of surfaces which are described by parametric equations. For example, r of uv equals 2 plus cosine v times cosine u, 2 plus cosine v times sine of u, and sine of v. And I could notice that if I plug in u equals pi over 4 and v equals pi over 4, I end up with the point the square root of 2 plus 1 half, the square root of 2 plus 1 half, the square root of 2 over 2. So this is some point on whatever surface this parametric equation is describing. And I can ask, okay, what's the local tangent plane at that surface? And it's actually really very easy to do. I can even draw a nice little graph of this particular surface, which has a very familiar shape. It looks a little bit like this. In particular, it's a donut shape. Or mathematically, we like to call that a torus, just so that we don't get hungry. And the point that I'm looking at is where x and y are the same, and z is root 2 over 2. So it's some sort of point like over here-ish on that surface. And I can think about the tangent plane, which is this guy coming right here, And I'm trying to find an equation for that tangent plane. Try to figure that out. Now, the nice thing that I can do about this is I could think about making a couple different curves on my surface which pass through this particular point. And the first curve I want to make by fixing my value of u and letting v vary. So I'm going to let u be fixed at pi over 4 and just let v change as we move around. And that's going to move, in this particular case, in a curve that goes around like this. That's the curve that's parameterized by r of pi over 4 v. So I only have one free parameter there, so it's not drawing a surface that time. The light blue is drawing a curve. It's just one-dimensional thing. Alternatively, what I could do is I could let u vary and keep v fixed at the value that I'm interested in, and make a curve r of u pi over 4. And in that case, if I plug that into my parametric equation up here, v is stuck at pi over 4, so in particular, the z value is fixed at root 2 over 2, but the u and the v values are changing. So in that case, what I'm ending up doing is I'm following my surface, passing through this point, and going around in a fun little circle like this. So these generate two different paths. And what I can do is if I take the derivative of either one of these parametric equations for those curves, that'll give me a vector in the direction of the tangent line to the curve. So in particular, if I take the derivative at this particular point where they intersect, I'm going to have a little tangent line, one in this direction, which will be a vector in my plane. And if I do the same thing for the light blue one, I'll have a vector in this direction, which will be in my plane too. So this is a really nice way to get two different vectors in my plane. Specifically, two vectors in my plane are just taking the derivative of the light blue curve, so that's ddv. It's a function of a single variable, so I can do regular derivatives, not partials, of r pi over 4 v at v equals pi over 4. And I can also do ddu of r of u pi over 4 at u equals pi over 4. Now, one thing that we might notice, of course, is that these are just the u and v derivatives, the u and v partial derivatives of the r vector. These are just, I'll call it r sub u at the value pi over 4, and r sub v at pi over 4. So I've got two different vectors that are in my plane. If I've got two vectors in my plane, I know a good way to get the normal vector of the plane. What can I do? I feel like this is on Blue's Clues. What should I do? I should take the cross product, right? So let's take the cross product of those two and get a normal vector. And that'll just be ru cross of rv. And I'm just going to evaluate that at the point pi over 4. And that'll give me a normal vector to the plane at the particular point. So once I have a normal vector, plus I have a point on the plane, which of course is the point that I started out with, I can easily write down the plane equation. That's something that we've done many times. But let's go ahead and give it a shot here. So what is r sub u? R sub u. So r up here was this equation again. Let me copy that. So r was equal to 2 plus cosine v times cosine u, 2 plus cosine v times sine of u and sine of v. So r sub u is going to be minus 2 plus cosine v times sine of u, 2 plus cosine v times cosine of u, and 0. And of course we can evaluate this at the particular point. At that point, pi over 4, pi over 4. And I'm getting r of u there equal to minus the quantity root 2 plus 1/2, root 2 plus 1/2, and 0. Similarly, we can get r sub v, and I can plug that in at pi over 4, pi over 4. And there I get r sub v is equal to the vector negative 1/2, negative 1/2, root 2 over 2. So my normal vector is just going to be given by taking the cross product of these two, which is going to be